Hello everyone and welcome to another video on our own devices. I'm Jean Messier and today we are having a look at a fascinating piece of lighting technology. This is a keychain containing what's known as a beta light. And despite appearances, this is not just any glow-in-the-dark phosphorescent knickknack. That is, this doesn't just absorb ambient light and slowly re-release it in the dark. Rather, this produces light continuously and can do so for up to 20 years without any batteries or other power source. This is because this is powered by the radioactive decay of a gas called tritium. And tritium is a fascinating material with a long history in the field of nuclear physics. So buckle in because we're going to be taking a deep dive into the history of this gas and all of its applications. Now, tritium is a heavy isotope of hydrogen. Regular light hydrogen, or protium, which makes up most of the matter in the universe, comprises a single proton and a single electron. Add a neutron to the nucleus and you get deuterium, or hydrogen 2. Now, deuterium plays a number of important roles in nuclear physics, most notably as a fuel in fusion reactors and as a neutron moderator in fission reactors, but that is a whole rabbit hole unto itself and far beyond the scope of this video. But if you want to learn more, please check out my comprehensive video on the CANDU reactor over on Today I Found Out, link in the description. Now add another neutron to deuterium and you get tritium, or hydrogen 3. Unlike protium and deuterium, tritium is radioactive, decaying via beta emission with a specific activity of 3.57 times 10 to the 14 becquerels, or 9,650 curies per gram, and a half-life of 12.33 years. In this process, one of the neutrons in the nucleus is converted into a proton, a neutrino, and a beta particle, effectively an electron. The beta particle and neutrino are emitted while the proton is retained, causing the atomic number to go up by 1 and the atomic mass to remain the same. Thus, tritium decays into helium-3, which, being stable, undergoes no further decays. Tritium also releases a negligible amount of X-rays in the form of Bremsstrahlung, German for braking radiation, and this is released when a beta particle is slowed down by collision with other particles and releases its extra energy as a gamma photon. Now, natural tritium is exceedingly rare, accounting for 1 in 10 to the 18th or 1 quintillion hydrogen atoms on Earth. Most natural tritium on Earth is produced by high-energy cosmic rays interacting with nitrogen atoms in the atmosphere. For this reason, it is most highly concentrated in rainwater. The overall radiation output from all natural tritium on Earth is around 1 exabecquerel, or 1 quintillion decays per second. Of course, today there is far more anthropogenic or man-made tritium in the environment produced by nuclear reactors and atmospheric nuclear detonations over the last 80 years, around 186 exabecquerels. Tritium was first discovered in 1934 at the Cavendish Laboratory at Cambridge University by Sir Ernest Rutherford, Mark Oliphant, and Paul Hartog. Using a linear particle accelerator designed by Ernest Walton and John Concroft, they bombarded heavy water, water in which one or more hydrogen atoms is replaced by deuterium, with deuterons, or deuterium nuclei. When they analyzed the products of their experiment, they discovered 2 species with an atomic weight of around 3, which they correctly identified as tritium and helium-3. However, when they then tried to concentrate and isolate the tritium, they were unable to do so. And it turned out that Rutherford had made something of an error. See, he had correctly predicted that one of the 2 weight 3 atomic species would be neutral and the other would be radioactive, but he mixed up which was which. So by the time he was able to concentrate his tritium sample, most of it had already decayed away. Now, this error wouldn't be realized for another few years by American physicist Luis Alvarez. Now, Alvarez had discovered large concentrations of helium-3 in underground deposits of natural gas, and he reasoned that either helium-3 had an extremely long half-life or it was perfectly stable. And in order to support his theory, generated tritium by bombarding a lithium target with neutrons, then reacting that irradiated lithium with water to produce hydrogen gas. In this manner, he was able to measure the beta radiation produced by tritium and, by comparing the activity of his sample with one produced by Rutherford in 1935, determined that the isotope had a half-life of around 12 years. And the timing of this discovery was fortuitous, for it would soon permit the development of the most powerful weapons known to mankind, thermonuclear weapons, aka hydrogen bombs. Now, the history of the development of the hydrogen bomb is a long and complicated one, and one which I cover in great detail in my video over on Today I Found Out. But in brief, Most nuclear warheads are of the implosion type. In this design, a spherical subcritical plutonium or uranium core or pit is surrounded by specially shaped lenses of conventional high explosives. When these explosives detonate, they produce a converging spherical shockwave that compresses the pit to critical density. At the same time, a neutron initiator inside the pit produces a burst of neutrons, kicking off the nuclear chain reaction. Now, the efficiency of implosion weapons, that is, how much of the nuclear material is actually converted into energy, depends mainly on how long you can keep the core together before the expansion caused by the release of fission energy blows the assembly apart and stops the reaction. And there are a couple of standard methods for increasing efficiency, the most common being to incorporate a spherical shell or tamper of heavy material like natural uranium around the pit. This holds the pit together via inertia, giving more time for the chain reaction to consume more nuclear fuel. Efficiency can be further boosted using a levitated pit design with a large air gap between the tamper and the pit. This way, the fissioning pit has to overcome not just the static inertia of the tamper, but also its inward momentum, further delaying its expansion. An alternative form of this design is a hollow pit, which allows the tamper to be discarded and results in a lighter, more compact warhead. Finally, many warheads contain a pusher, a hollow shell of light material like aluminum or beryllium located between the explosive lenses and the tamper. This reflects part of the shockwave away, slowing down the compression of the pit and increasing efficiency. However, even with all of these techniques combined, there is an upper limit to the efficiency that can be achieved, around 20% for a pure fission weapon. This, in turn, places an upper limit on explosive yield, with the current record being held by the 500 kiloton Ivy King device detonated over Eniwetok Atoll on November 16, 1952. Containing a whopping 60 kilograms of high-enriched uranium, this was a highly inefficient design and approached the upper size and weight limit for a practically deliverable weapon. However, even before the first atomic bomb was detonated, scientists began to theorize that the explosive yield could be increased by an order of magnitude or more using nuclear fusion. Not only is fusion fuel, hydrogen, far more abundant and cheaper than uranium or plutonium, but fusion produces a burst of neutrons, which can then be directed back into the weapon's core, boosting fission and making the increase in explosive yield almost limitless. Now, the process of nuclear fusion that takes place in stars, in which light hydrogen is fused into helium, was first worked out in 1937 by German physicist and later Manhattan Project member Hans Bethe. But it wasn't until 1941 that Italian physicist Enrico Fermi first suggested that a conventional nuclear explosion could be used to trigger a fusion reaction, releasing significantly more energy. This idea caught the imagination of Hungarian physicist Edward Teller, who famously began working on the super bomb, or simply super, to the neglect of his actual Manhattan Project duties. Early on, Teller realized that the process of stellar nuclear fusion using light hydrogen was ill-suited to the production of a thermonuclear weapon. This is because hydrogen nuclei are ordinarily repelled by electrostatic forces and will not fuse unless placed under enormous temperatures and pressures, conditions that are not practically achievable even using nuclear weapons. However, fusion using heavy hydrogen isotopes, deuterium and tritium, held far more potential, because the extra neutrons contribute strong nuclear force, which can pull those nuclei together and permit fusion. Much easier to achieve than light hydrogen fusion was a reaction combining two deuterium atoms to produce helium-3, 1 neutron, and 3.3 mega-electron volts of energy. While even easier and more energetic was a reaction combining deuterium with tritium to produce helium-4, 1 neutron, and 17.5 mega-electron volts of energy. Now, Teller initially assumed that the design of the super would be relatively straightforward, and his early concepts involved either wrapping the fusion fuel around a regular nuclear warhead or layering the fusion fuel and either uranium or plutonium to create a composite core. And he called this the alarm clock design, but the same design was independently conceived by Soviet nuclear physicist Andrei Sakharov, who dubbed it the Sloika after a Russian layer cake. Unfortunately, Teller began to run into problems. For instance, around 80% of the energy released by a nuclear weapon is in the form of X-rays, to which hydrogen is transparent. This meant that this energy would not be available to compress and ignite the fusion fuel. Now, the other 20% of this energy is in the form of heat and the shock wave, but unfortunately, these were not fast enough to adequately compress and ignite the fuel. By the time adequate compression was achieved, the bomb would have blown itself apart. Furthermore, heat added to the fusion fuel would have escaped at the exact same rate, so it never would have accumulated the energy needed to ignite. There is also the problem of the fusion fuel itself. Tritium at this point was extremely rare and extremely expensive, being produced only in small quantities in nuclear reactors, and the amount needed for a classical super would have made the weapon exorbitantly expensive. Now, just like Luis Alvarez had done in 1939, it was possible to breed tritium from lithium by neutron bombardment, but here again, Teller ran into a roadblock in that in terms of neutron efficiency, it's far more efficient to use your neutrons to breed plutonium from natural uranium than it is to produce tritium from lithium and then fuse it. No matter what he did, he kept on reaching dead ends and soon began to wonder whether the super wasn't impossible to build after all. And even if it was possible, it would have been so enormous that, as J. Robert Oppenheimer quipped, it could only be delivered by ox cart. However, Teller's early work didn't go to waste, as it was soon adapted into a technique for increasing the yield of nuclear weapons called fission boosting, in which a 50-50 mixture of gaseous tritium and deuterium is injected into the weapon's hollow pit just prior to implosion. This triggers fusion, which then releases a flurry of neutrons, which trigger more fissions within the pit, increasing the yield of the weapon. And since the amounts of deuterium and tritium needed are much smaller than in the classical super, this type of weapon is far more economical to produce, and it's far more economical to top up the tritium in the reservoir as it decays away. Fusion boosting was first tested in the George test of Operation Greenhouse at Eniwetok Atoll, in which an ordinary warhead was wrapped in a donut-shaped reservoir of liquid deuterium and tritium. Detonated on May 8, 1951, this device generated a yield of 225 kilotons. This was immediately followed by the item test on May 24, 1951, in which a gaseous deuterium-tritium mixture was injected directly into the hollow core. This yielded 45.5 kilotons, twice that of the standard unboosted warhead. Fission boosting allowed nuclear weapons to be made smaller, lighter, more efficient in their use of nuclear material, and far more flexible. As the degree of boosting is directly related to the amount of deuterium and tritium injected into the core, this allows the production of variable yield weapons, also known as dial-yield. The smallest known nuclear weapon to be deployed, the W-54 warhead, was a boosted device with a yield adjustable between 10 and 1,000 tons of TNT. It was used in the AIM-26 Falcon air-to-air missile, the Davy Crockett recoilless rifle, and the Special Atomic Demolition Munition, or SADM. And to learn more about the latter, once again, please check out my video on the subject over on Today I Found Out. The largest non-thermonuclear weapon ever tested, the 720 kiloton British Orange Herald, was also a boosted device. But while extremely useful, fission boosting didn't allow for the near limitless magnification of explosive yield that Teller had originally envisioned. Now, the Soviets did actually test the alarm clock or Sloika design, also known in the USSR as Sakharov's first idea, in the form of the RDS-6 device detonated at the Semipalatinsk test site in Kazakhstan on August 12, 1953. However, this produced a yield of only 400 kilotons, around 15 to 20% of which came from fusion, and as Teller had predicted, the design was not scalable. Now, after years of fruitless calculations, in 1951, Teller teamed up with Polish mathematician Stanislaw Ulam, and the two soon made a major breakthrough. See, what they realized was that while the shockwave and the heat from a nuclear weapon was not fast enough to initiate proper nuclear fuel compression, nuclear weapons did produce something that was X-rays, which not only travel at the speed of light, but also make up 80% of the energy released by the weapon, as we discussed before. Now, their new design for the super, now known as the Teller-Ulam Design, worked on the novel principle of radiation implosion. The basic Teller-Ulam design comprises three basic components: the primary stage or trigger, which is a regular fission bomb, a secondary stage containing the fusion fuel, and an interstage to channel X-rays from the primary into the secondary. The secondary comprises, from outside to inside, an outer radiation case, a thick cylinder of natural uranium called the tamper, and a central cylinder of plutonium called the spark plug. The space between the tamper and the spark plug is filled with fusion fuel, typically in the form of solid lithium deuteride, while the space between the tamper and the radiation case is filled with some sort of plasma-generating material. In early weapons, this was polystyrene foam, but in current U.S. thermonuclear weapons, it is a highly classified material codenamed fog bank, widely believed to be some sort of aerogel. Anyway, when the primary detonates, X-rays are channeled through the interstage into the space inside the radiation case, where they are absorbed by the tamper. This causes the outer wall of the tamper to heat up and ablate, shooting material outwards and creating an opposite reactive force that causes the tamper to collapse collapse inwards and compress the fusion fuel. At the same time, the X-rays convert the material between the tamper and the radiation case into hot plasma. This serves two purposes. First, the plasma insulates the inner wall of the radiation case, preventing it from ablating and prematurely blowing the secondary stage apart. And second, being transparent to X-rays, it maintains an open channel for X-rays streaming from the primary. Now, the collapsing tamper not only compresses the fusion fuel, but also the spark plug, causing it to reach critical density and undergo nuclear fission, further increasing the temperature and triggering fusion in the lithium deuteride fuel. This fusion, in turn, produces a flurry of neutrons that boosts fission in both the spark plug and the tamper, creating a feedback loop that generates more and more energy until the expansion of the fusion fuel overcomes the momentum of the collapsing tamper and the secondary blows itself apart. Now, the Teller-Ulam design not only releases far more energy than fission boosting or classical super designs, but it's also infinitely scalable. See, if you add another fusion stage after the secondary, the X-rays produced by the secondary stage will initiate the same radiation implosion in the tertiary. And you can continue doing this ad infinitum, making the yield as big as you want it to. Indeed, the largest nuclear device ever tested, the Soviet Tsar Bomba, was a three-stage device. Detonated over Novaya Zemlya Island in northern Russia on October 30th, 1961, the bomb produced an explosive yield of a whopping 50 megatons. More disturbing still, that was only half its maximum theoretical yield, as at the last minute, Soviet scientists replaced the secondary stage's uranium tamper with non-fissionable lead in order to limit radioactive fallout. Now, the first test of the Teller-Ulam design took place during the Mike shot of Operation Ivy at Eniwetok Atoll. For its fusion fuel, the Mike device used 1,000 liters of liquid deuterium, which needed to be kept at temperatures below minus 253 degrees Celsius or 20 Kelvin. This, in turn, required the construction of a massive cryogenic plant, causing the whole device or assembly to weigh a whopping 74 metric tons. This, of course, was not a practical deliverable weapon, but this was not a problem, as the test was designed for ease of analysis and to prove the feasibility of the Teller-Ulam design. The Mike device was detonated on November 1st, 1952, producing an explosive yield of 10.4 megatons. With the basic Teller-Ulam principle proven, U.S. scientists next moved on to a far more practical dry fuel design using solid lithium deuteride, dubbed the shrimp device. This was tested on March 1st, 1954, as the Bravo shot of Operation Castle at Bikini Atoll. Now, while the Bravo device was predicted to have a yield of around 5 megatons, to everyone's shock, this tripled to 15 megatons, damaging a large amount of equipment, sending a giant plume of radioactive fallout across the Pacific, and sparking an international incident, often considered the world's first major nuclear disaster. As it turns out, the physicists who had designed the shrimp device had made a fundamental error. See, the lithium deuteride used as the fusion fuel contained 40% lithium-6, with the remainder being lithium-7. It was expected that the lithium-6 would absorb a neutron and split into helium-4 and tritium, the latter of which would then fuse with the deuterium. Meanwhile, lithium-7 was not expected to participate in the reaction at all. Rather, it would absorb a neutron to become lithium-8, which would decay via beta emission into beryllium-8, which would in turn decay via alpha emission into helium-4. All this would take place over the timescale of around 1 second, far longer than the actual thermonuclear reaction. However, the Castle Bravo test revealed that when lithium-7 is bombarded with neutrons with energies greater than 2.5 mega-electron volts, it instead fissions into tritium, helium-4, and a free neutron. This extra tritium fuses with deuterium while free neutrons boost the ongoing fission processes, greatly increasing the overall yield of the weapon. Now, while the gigantic IV Mike device was never intended to be a practical deliverable weapon, in case the dry fuel Bravo device didn't work or took longer than expected to develop and weaponize, the US actually did develop a deliverable wet fuel bomb called the Mark 16 or the Jughead. Just like the Mike device, this was fueled by liquid tritium and deuterium, which would have been topped up from Dewar flasks or thermoses carried aboard a specially modified Convair B-36 Peacemaker delivery aircraft. The Jughead was intended to be tested in the Yankee shot of Operation Castle, but following the success of Castle Bravo, this was canceled, and the solid-fueled Runt 2 device was detonated instead. Now, just like the alarm clock or Shloika device, the Teller-Ulam design was also independently created by Andrei Sakharov and known as his third idea. And if you're wondering what his second idea was, that was the idea of breeding tritium from lithium deuteride. Now, the first true Soviet staged thermonuclear weapon, RDS-37, was tested on November 22, 1955, and produced a yield of 1.6 megatons. Today, effectively all thermonuclear weapons use some variation of the Teller-Ulam design, while due to the method's efficiency and scalability, nearly all deployed nuclear weapons are either boosted fission or thermonuclear devices. And that is a brief overview of the history and technology of thermonuclear weapons, or at least as brief as I can make it. Now, the story of the hydrogen bomb involves a lot of complicated and fascinating politics, but for this video, I decided to stick to the technical details. Again, if you want to learn more about the entire story, please check out my video over on Today I Found Out. Now, while nuclear weapons applications account for the vast majority of tritium produced today, that is far from the gas's only application. And finally, we get to the ostensible subject of this video, tritium lighting. Now, radioluminescent lighting has been around for over 100 years, with the first practical application being a series of luminescent paints based on the 1903 patent of Dr. George F. Kunz, and marketed under various brand names like Undark, Luna, Marvelite, and Radiolite. These paints are based on the isotope Radium-226, which decays via alpha and gamma emission with a specific activity of 3.7 times 10 to the 10 becquerels, or 1 curie per gram, and a half-life of 1600 years. In this type of decay, the nucleus emits an alpha particle, 2 protons and 2 neutrons, aka a helium nucleus, causing the atomic number to go down by 2 and the atomic mass number to go down by 4. Thus, radium-226 transmutes into radon-222. In luminous paint, radium was mixed with a binding agent and a phosphor, typically zinc sulfide, which converted the energy from the alpha particles emitted by the radium into visible light. These phosphors could, in turn, be doped with various elements to produce different colors. For example, copper yielded a green light and copper manganese a yellowish-orange light. Radium paint was widely used to coat the dials of watches, clocks, aircraft instruments, and other devices up until the 1960s, when it was largely phased out for safety reasons. See, radium-226 emits significant amounts of gamma radiation, which can easily penetrate the glass and metal bezels of clocks and watches. Indeed, wearing a radium dial wristwatch continuously would expose you to around 24 millisieverts per year, 20 times the U.S. Code of Federal Regulations' maximum annual dose for ordinary citizens. Even worse, if radium-226 manages to get inside the body, it can wreak absolute havoc. The most infamous case of this was the so-called Radium Girls, young women hired by companies like the United States Radium Corporation in the 1920s to paint luminous clock and watch dials by hand. These women were not only not informed of the dangers of radium, but were also instructed to lick their paintbrushes to achieve a sharper point. As a result, they absorbed large quantities of radium, leading to horrific health effects ranging from aplastic anemia and various cancers to so-called radium jaw, in which the radium was absorbed into the bones of the women's jaws and literally caused them to rot away and fall off. Today, there are plenty of old radium dials about, but none of them glow anymore. Not because the radium has decayed away. With a half-life of 1600 years, it is still very much radioactive, but because constant bombardment by alpha particles progressively degraded the zinc sulfide phosphor. So if you come across something coated in radium paint, be very careful with it. While the gamma radiation shouldn't be too much of an issue unless you keep the item close to your body for long periods of time, ingesting or breathing in the dust from the crumbling paint can be very hazardous. So wear gloves and a mask and wash your hands afterward. Now, a number of other isotopes have briefly been used in luminous paint, including promethium-147, which decays via beta emission into samarium-147 with a specific activity of 34,300 gigabecquerels per gram and a half-life of 2.62 years. Not only does this isotope release significantly less gamma radiation than radium, but beta particles do far less damage to zinc sulfide than alpha particles, giving it a longer service life. Furthermore, the short half-life meant that expired paint could be safely disposed of. However, this also gave promethium paint a very short service life, meaning it was largely used in short-term applications like the switches aboard the Apollo spacecraft or the sights on the M72 LAW single-use anti-tank rocket launcher. Another isotope used in radioluminescent lighting was strontium-90, which decays via beta emission into yttrium-90 with a specific activity of 5.21 terabecquerel, or 141 curies per gram, and a half-life of 28.79 years. However, like radium, strontium-90 is easily incorporated into the bones and is considered to be a dangerous fission product and environmental contaminant in the wake of above-ground nuclear detonations and nuclear reactor accidents, such as Chernobyl. For this reason, its use in luminous paint has been brief and controversial. Indeed, in the early 1960s, Rolex became the subject of an Atomic Energy Commission or AEC investigation when a few hundred GMT master watches purchased in Singapore were found to contain strontium-90. A few customers even sued Rolex, claiming that strontium leaked out of the watches and inflicted radiation burns and other injuries. In at least one case, it was later determined that a young boy who had burned himself playing with a lighter had blamed his father's watch in order to avoid getting in trouble. Interestingly, the non-radioactive isotope strontium-88 is still widely used in clocks and watches in the form of the non-toxic compound strontium aluminate, which is the main component of regular phosphorescent or glow-in-the-dark paints and plastics. Anyway, by the 1960s and 70s, the standard isotope for use in radioluminescent lighting had become tritium, which combines the advantages of extremely low gamma radiation and a relatively long 20-year half-life. Gaseous tritium light sources, or GTLSs, also known as beta light, were first patented on October 29, 1953 by Edward Shapiro, working for Tracerlab Incorporated of Cambridge, Massachusetts. These consist of small borosilicate glass tubes filled with a small amount, around 67 gigabecquerel or 1.8 curie, of tritium and coated on the inside with a phosphor, again typically doped zinc sulfide or zinc orthosilicate. Now, borosilicate glass is most commonly used because it is very resistant to breakage and is also able to easily block the beta radiation emitted by the tritium. Now, the small amount of gamma radiation can penetrate, but as I said before, this is insignificant. Now, for further protection against breakage, GTLSs are usually embedded in plastics, as in this keychain, with a component containing one or more GTLSs being known as a gaseous tritium light device, or GTLD. Now, all sorts of devices have been fitted with tritium lights, including keychains like these, emergency exit signs, compasses like the US military's M1950, fishing lures, though these are banned in most jurisdictions, sights for all sorts of weapons from pistols to rocket launchers, and of course, clocks and watches. Now, many sources claim that the first company to produce commercial tritium dial watches was Italian luxury watchmaker Officina Panerai, which began marketing the technology under the brand name Luminor in 1949. However, this is not the case. Not only was tritium lighting not patented until 4 years later, but it would have been impossible for Panerai to get its hands on commercially viable quantities of tritium during this period. See, as we discussed before, the only real sources of tritium are from nuclear reactors or particle accelerators, neither of which were present in Italy until the 1960s. Nor could Panerai have imported tritium from elsewhere. See, due to tritium's key role in boosted fission weapons, both the United States and the Soviet Union invested vast resources into producing enough of it to supply their own arsenals. For example, starting in 1951, the AEC began construction of the 800 square kilometer Savannah River plant in South Carolina, where they built 5 heavy water moderated reactors to produce tritium. The plant became fully operational in 1955 and supplied most of the US's tritium needs at a rate of around 10 grams a year until 1988. As a result, for many years, what tritium was available for private use, such as in scientific research, was exorbitantly expensive, around 10 cents per microcurie in 1953. Given that the average wristwatch uses around 25 millicuries of tritium, a luminous watch made during this era would have cost nearly $25,000 in tritium alone. For this reason, it wasn't until the 1960s that affordable tritium dial watches began to appear on the market. Today, the cost of tritium is around $3 per curie. All this to say, Panerai's Luminor had nothing to do with tritium. Rather, it was a brand name for a regular Radium-226 luminous paint trademarked in 1949. This is a follow-on from the company's previous Radium brand, the name of which was derived from radiation, and mire or mira, which is French or Italian for sight. And indeed, this paint was most famously used on torpedo aiming sights for the Italian Navy. Now, while today tritium is most closely associated with watches and clocks, its use in this application was actually banned in Germany and Switzerland in the 1990s, and its use in consumer timepieces has gradually faded away outside of specialized military pieces. And this is in spite of the relative safety of tritium lights. Indeed, a piece like this will deliver only around 20 milligraves per hour if held right up against the skin. And if you want to learn more about the complicated system of radiation dose rate units, such as Grays, Sieverts, Röntgens, and Rads, please check out my video on the subject, again, over on Today I Found Out. Now, if this is broken open and you inhale the tritium, then it can be dangerous. But thankfully, being hydrogen, tritium disperses very rapidly in air. It also has a relatively short half-life inside the human body of around 7 to 14 days. So if you do manage to damage one of these somehow, clear the room and let it air out for a couple of minutes before re-entering. Now, most commercial tritium lights consist of individual GTLS tubes. However, I found at least one patent for creating tiny glass microspheres containing tritium and phosphors, which can be mixed with a medium to produce radium-style luminous paint. This, in turn, can be used to paint wash dials and other equipment, or conceivably even paint the walls of your house to deliver continuous illumination, though why you'd want to is beyond me. Now, tritium, of course, has many other applications outside of nuclear weapons and tritium lights. For example, it is a key component in many schemes for nuclear fusion power, including the International Thermonuclear Experimental Reactor, or ITER, and the National Ignition Facility, or NIF. And given its short half-life, both radiological and biological, tritium is also widely used as a tracer in biology, ecology, and in medical diagnostics. And since tritium is most highly concentrated in rainwater, it can be used to estimate the age of products made with that water. For example, in 1954, American chemist Willard Libby determined that tritium levels could be used to estimate the age of vintage wine, since the finite amount of tritium in the wine when bottled will decay away at a known rate. By the same logic, if wine contains higher than natural concentrations of tritium, that means it was bottled after 1945, a fact that can be used to spot forgeries. Finally, tritium is used to ionize the working gas in some high-voltage electron switching tubes and is being investigated for use in so-called beta-voltaic cells or nano-tritium batteries, which convert beta radiation directly into electricity similarly to a photovoltaic cell. Now, the global commercial demand for tritium is around 400 grams or 3.8 megacurie per year, with most being produced in commercial nuclear reactors. For example, the 17 operational CANDU heavy water moderated reactors in Canada produce an average of 2 kilograms of tritium per year, which is extracted at the tritium removal facility at the Darlington Nuclear Generating Station in Bowmanville, Ontario. This tritium would ordinarily be an unwanted byproduct and environmental pollutant, but such facilities allow it to be collected and sold for commercial or research use. And that, dear viewers, is a brief summary of the physics, chemistry, and applications of tritium, a remarkably fascinating and versatile substance. So a bit of a long one today, but I felt that my last take on the subject was not detailed enough, and I wanted to be extremely thorough. And sorry for the delay in getting this one released. It took a lot longer to produce than I thought it would, and I've been busy with a bunch of other projects. Anyway, thank you so much for watching. I'll see you next time in another video where we'll look at yet more fascinating radioactive artifacts and other devices just like this one. Until then, I'm Jean Messier from Our Own Devices. Have a great day.